because from time to time, science and math intertwine, and this is one of those things. Because oftentimes in science, you deal with very, very large or very, very small numbers. If you're talking about the distance, for example, from the Earth to the Sun, that number is very, very large. It is 491 billion. Yes, you do. 491 billion feet from the sun. That's a big number. Lots of zeros there. Okay. Nolan, yes.
Do you know Mr. Moore's class is actually over?
We're going to over.
It's done.
Oh, you already been there?
No science.
Yeah, I'm saying we're going to learn with science and math.
You were doing
today,
math
right?
and
No,
science.
yeah, it's interchangeable.
Like today.
Anyway, let's write this number a second time. 491 billion. Okay. And let's do it again. Practice making those circles. 491 billion. If you were writing an essay on the distance of the sun from the Earth, you would have to write 491 billion, something like 491 billion times. Okay? The same would be true if you were like measuring the radius of a molecule, right, or a cell, or something really, really, really super small, which you deal with in science a lot. Okay, and so we have what's called scientific notation, which is basically a way to write very large and very small numbers using powers of 10. It's a way to write very large or very small numbers using powers of 10. And I say, and this is where the math comes into play here, because when we talk about powers of 10, what happens when you multiply something by 10? Like if I ask you for, let's do it over here, 6.1 times 10, what's the answer to that? Dominic. Whoa, quick math. How'd you go that so fast? Right. All that's really happening when you multiply something by 10 is the decimal gets moved over to the right one spot. So 6.1 times 10 equals 61. Let's say we have 3.598 times 100. Now 100 is a power of 10, right? 10 goes into 100, okay? How many times would you need to move that decimal over to get to the answer here? Twice, because how many zeros are there?
Two.
And so your answer here would be 359.8. The numbers really don't change, okay? It's just that act of multiplying by 10 causes the decimal point to move over. That's why learning your tens back in third grade was super simple. You know, if you were asked for 9 times 10, everybody? 90, because what's happening here, the decimal point on this 9 comes after it. We don't write it because there's nothing after that. But when you multiply by 10, you're still moving it over to the right. And then what do you fill that empty space with? A 0. That's how you get 90. That's why 9 times 100 is 900. 9 times 1,000 is 9,000, right? For every 0 that you have, the decimal point just gets kicked over once to the right. And that's kind of the math behind why scientific notation works. Well, let's practice a little bit. Okay? We've got a big number, like 5,670,000. Now, the key to scientific notation is to move the decimal until there's only one non-zero digit before the decimal. So in this case, 5,670,000, where's our point? Where's the decimal here?
After the 5. After the 6. The 7? After the 0. After the other 0.
At the way in,
yeah.
Right? 5,670,000. There's no decimal point that you can see, which means it's at the end. And so what scientific notation says is we need to move this until there's only one non-zero digit before it, which would be between the 5 and the 6. Right? If we put it between the 6 and the 7, then we have 5, 6 point. We don't want that. We want 5 point, only one non-zero digit. And so our number, we put the 5, we put the decimal, all the non-zero digits get written, the 6 and the 7. This is the only time you'll ever see me use an X to show that you are multiplying, because that's what scientific notation says to do. All right? It's a science thing, right? So we have to follow it. But how many times would we have to multiply this number, 5.67, by 10 to get back to our original number of 5,670,000? Put it another way, how many times did we have to move the decimal to get where we're at?
6.
6. Right? We had to move it 1, 2, 3, 4, 5, 6, which means we'd have to multiply by 10 6 times to get back to the original number. 5.67 times 10 to the 6th means we have to multiply by 10 6 times, or move this decimal to the right 6 times to get back to what we started with. And when you're talking about super duper big numbers, this is much quicker than writing out 491 billion times. Okay? So that's why scientific notation exists. And if you've ever used on your calculator and the answer that you have is super, super, super big, and it says like times 10 on the end, do you know what I'm talking about? That's scientific notation, right? That's your calculator giving you an answer in this form because your answer is so big. All right. Good so far? See what's going on here? Yeah.
Can I do the next one all by myself?
Not for the MCU, no.
No.
Okay. This next one though, 878 trillion. What two numbers is our decimal point going to end up between? Right now it's at the end, right? What two numbers will it end up between when we write it in scientific notation? Mia?
8 and 7.
8 and the 7. So 8.78. All those non-zero digits need to be written there. And the question is, how many times do we have to multiply by 10 to get it back to the original number? And this is where commas are helpful, because when you've got all those zeros there, it can be tough to 1, 2, 3, 4, 5. Every comma that you see is a group of 3 jumps, right? 3, 6, 9, 12, 13, 14. 14 moves to get it between the 8 and the 7, which means we have to multiply by 10 14 times to get it back to the original number of 878 trillion. Right? One common mistake that folks make with scientific notation, I saw with my other algebra class as well, is that people mistakenly think the power means how many zeros the number has. That's not the case. This number only has 4 zeros, yet our exponent is a 6. The reason why is because we've got 2 non-zero numbers that we have to include when we make the jumps. This number does not have 14 zeros. It's got 12. But it took 14 jumps to get the decimal where we want it to be. Okay? Now this question here, why is the exponent positive? What does a positive exponent in scientific notation tell you about your original number? Is it a really big number or a really small number?
Really small. Big.
Really big. 5,670,000, that's big. 878 trillion, that's big. When you've got a positive power on your scientific notation, it means the number is big. Number is big. It also means that you are multiplying by 10. Okay? Your original number is big and you're multiplying by 10.
It went up before.
So the next two, numbers you can see are very small. 0.00013 is a very small value. So how do we differentiate between a big number and a small one? Okay, we still have to move this decimal so there's only one non-zero digit before it, which means we've got to move it between the 1 and the 3. But how do we show with scientific notation that we're going to have to move our decimal backwards to the left to get to the original very small number? Anthony, what do you think?
Divided.
Okay, so we're going to have to divide by 10. What exponent would show that you're dividing by 10?
4.
Now,
Negative or negative?
a negative power. Okay, so we move this 4 times. This would be 1.3 times 10 to the negative 4. That negative 4 tells you that your number is very small, as 0.00013 is, and it tells you that to get back to this original number, right? If you saw this in scientific notation, you would know that to get back to the original, you have to move it to the left 1, 2, 3, 4 times and fill all of those empty spaces in with zeros. And you get 0.00013. Okay? The next one. What two numbers is our decimal point going to move between?
0 and 1.
Not the 0 and the 1.
What? Wait.
Because that would leave the 4, the 9, and the 0 before. It's going to be between the 4 and the 9. Only one non-zero digit is allowed before the decimal. So we're going to move all the way between the 4 and the 9. Okay? We do have to write the 0 and the 1 also. This 0 needs to be included because it's not at the end of the decimal. It's stuck between two non-zero, the 9 and the 1, so it needs to be included. Okay? But 4.901, how many movements did it take?
Negative 7.
Took 7 moves to get there. So to get back to the original number, we're going to have to divide by 10 essentially 7 times to get it back here, which means our exponent needs to be negative. Right? So 4.901 times 10 to the negative 7. So what does a negative exponent tell us? Zoe, tell us again. What does a negative exponent tell us? Josie, it's a small number. Your original number is very, very small. Okay? And essentially, mathematically, what's going on here is we are dividing by 10. Because when you divide by 10, it moves the decimal to the left. Just like multiplying by 10 moves the decimal to the right. Multiplication and division are opposites. They're going to have opposite effects. Okay? Can't wait for you to go to science class and you start talking about big and small numbers and you'll be like, we know scientific notation. My favorite day. Questions so far? Okay. We got about 5 minutes left, so here we go. The first section, you need to rewrite these numbers in standard form. So now we're going from scientific notation back to the original. So 7.613 times 10 to the 4th. Which direction is this decimal going to be moved?
To the right.
To the right, because the power is positive. How many times will we move it to the right? 4. Doesn't mean the number has 4 zeros. That's how many times we're multiplying by 10. That's how many times our decimal 2, 3, 4 gets moved. And what number do we add in that now new empty space?
0.
0. So our final answer is 76,130. But positive power means you're moving to the right to get back to the original. Okay? And how many times did you move it? 6.8 times 10 to the 10th. Which direction and how many times?
Right 10 times.
Right 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All those empty spaces get filled in with zeros. How many zeros do we have there? 9. Why does that make sense that we have 9 zeros if our power is 10?
Because there's 8.
Because the 8. We had to move once to get to the other side of the 8. Then we start adding zeros. So remember, the exponent is not how many zeros there are, it's how many movements there are. And because there was that non-zero digit, that 8, to jump over first, that means there's 9 movements left, and thus we have 9 zeros. 5.1973 times 10 to the 7th. Which direction are we moving the decimal?
Left.
Left. How many times?
7.
7. Right? So 5.1973. 1, 2, 3, 4, 5, 6, 7. 0, 0, 0, 0, 0, 0. If you want to put the 0 in front of the decimal, you can. It's not required. It means the same thing, whether it's there or not. And I'm not a teacher that cares one way or the other. So you can have 0 points. That, or just 0.00000051973. Either way is fine. But notice our number is very small, as it should be, because our exponent is negative. We got to move to the left. Okay. Lastly, 8.21 times 10 to the negative second. Write the answer down yourself. Don't say it aloud. But I'll give you like 15 seconds. Look at the exponent. Which direction? How far? Fill in the zeros.
Oh my gosh.
And who's confident? Maybe someone haven't heard yet today. Who's confident and would like to share? Someone you have not heard from yet, perhaps. I've heard from you, thank you. 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 Anybody? Everyone feeling brave? Tristan?
I ended up getting 0.821.
0.0821, right? Because when you move it over twice to the left, you do get that extra space there before after the point. You fill that in with a 0. Okay? Your other option would simply be 0.0821. The 0 to the left of the decimal doesn't have to be there. The 0 to the right of the decimal before the 8, that does have to be there. Okay? Your homework for tomorrow, for Monday, I lied. Monday is the second page here. The whole thing, the first 8, you're going to scientific notation, like the first 4 examples we had. The second 8, you're going from scientific notation to standard form, like the second set of examples that we had here. A word problem and review. Con due tonight, this due Monday, retake day tomorrow. That's what I'm at.